Hello students. Today our new and most interesting as well as important topic about some basic concepts about optical isomerism. As we know that in the case of isomerism we classified into two parts, structural isomerism and stereoisomerism. So in the case of stereoisomerism further classified into two parts, conformational analysis and configurational analysis. So in configurational analysis, which is also subclassified into two parts, geometrical isomerism and optical isomerism. I think so most of the isomerisms except these optical isomerisms we studied in a deep manner, right? Now today our mostly focus on optical isomerism. What is optical isomerism? Because it's a most important topic and it's a 3D topic, because in space how the structure we can arrange and what the characteristics of this optical isomerism that we have to study in this point. Why optical isomerism is required in this lesson? Because we know that in the case of SN2 reaction, these SN2 reactions which proceeds with a complete inversions of configurations, as we know that it's a Walden inversion, it's an example of a umbrella, right? So in the case of, because we know that in the case of an umbrella turns inside out in a strong wind, it's an inversions of a configuration is called as a Walden inversion. So to study about the Walden inversions, then while in SN1 reactions which proceed with racemisation, it's what is the terminology racemisation that we have to understand in this topic. To understand this concept we must know some basic principle of stereochemistry and the terms such as plane polarized light, number 1, optical activity, number 2, enantiomerism, number 3, chirality, number 4, retention, number 5, inversions, number 6, and racemisation is number 7. Right? So these are our main menu in this topic. So we start with a plane polarized light. So what is the meaning of plane polarized light? In standard 12 physics, there is one topic is a polarized light. But in chemistry, we know that in ordinary light, right, which consists of electromagnetic waves, because as we know that light is the electromagnetic waves, it's electromagnetic radiations of a different wavelengths, which can be starts with a radio wave to microwave, right? So all different wavelengths. So it's a polychromatic light. The meaning of polychromatic light means what? So it having a different types of wavelength. But monochromatic light on the other hand consists of wave of only one wavelength. Only one wavelength. So according to one wavelength, so what we have to do? What we have to do in this case? Right? So it can be obtained either by passing the ordinary light, means white light, through a prism, or some gratings is also used, or by using a source which gives a light of only one wavelength. For example, if sodium lamp emits yellow light of about 9.3 nanometer wavelength, whether it is ordinary light or monochromatic light, it consists of wave having oscillations or vibration in all the plane. Right? First, what we have to do? First, we convert polychromatic light into monochromatic light, and after this polychromatic light, which is converted into monochromatic light, this monochromatic light consists of waves having oscillation or vibration in all the planes, perpendicular to the line of propagation of light. So, if such a beam of light is passed through a Nicol prism, there is one prism. Which can be American scientist Nicol first test made prism is called as a Nicol prism, which is made from a particularly crystalline form of calcium carbonate, sometimes known as calcite 2. So the light that comes out of the prism has an oscillation or vibration only in one plane. So in this case, first we want to prepare a plane polarized light. First we convert polychromatic light into monochromatic light with the help of prism, and then after we have to convert this monochromatic light into such a light of polarized light. In polarized light is nothing but it's a simple way that your oscillations or vibrations is only in the one plane. Such a beam of light which has vibration only in one plane is called as a plane polarized light. It's a plane polarized light. In simple manner, this is the ordinary light. So this ordinary light, when you see that this ordinary light, in this case only one wavelength, but they oscillating or their vibration in a different plane. But if we pass through the Nicol prism, so it's converted into a single plane polarized light. So we require this plane polarized light. So after the plane polarized light, next our topic, because our topic is now it's optical activity. The optical activity. So what is the meaning of optical activity? So in the case of optical activity, certain substance which rotate the plane of polarized light. What is the meaning of plane polarized light? Plane polarized light is a beam of light which has vibrations only in one plane, right? It's called as a polarized light. So when certain substance rotate this plane polarized light, when the plane polarized light is passed through their solution. For example, if I having a certain compounds, if I pass through a plane polarized light, so which rotate the plane of this light, it means that our compound is optically active compound. So such a substance which can rotate their plane of polarized light are called as an optically active substance. And the property of such a substance to rotate the plane of polarized light is called as an optical activity. So the angle through which the plane of polarized light is rotated is measured by an instrument which is called as a polarimeter. So in a simple manner, first we have a light source. This light source, we know that the light source is a sodium lamp. So this light is monochromatic in itself in nature, because in the case of this sodium light, we have a 589.3 nanometer light, so it's a monochromatic light itself. But this monochromatic light which can be rotated through a different planes. So we pass through the Nicol prism, and this Nicol prism is sometimes called as a polarizer. It's called as a polarizer. Now we get a plane polarized light, and this plane polarized light which can be passed through such a some compound, it's a polarimeter tube, right? So if we pass through the polarimeter tube, so our light, this light which can be either rotate clockwise or anti-clockwise, right? So the angle of this alpha, so if they rotate from rotate in the right hand side or left hand side, so this rotation which can be measured with a movable Nicol prism, sometimes called as an analyzer. So this whole system is called as a polarimeter system, where you have put such a type of substance which rotates the plane of polarized light towards right, means clockwise, is called as a dextro-rotatory. The Latin word means dexter means right hand side, and is represented by a algebraic sign is plus. On the other hand, a substance which rotates the plane of polarized light towards the left means anti-clockwise, right? Is called as a levo-rotatory. Levos means left, and which is presented by a algebraic sign is minus. So it's a plus minus. Sometimes we write like a D and L, dextro and levo 2. So such a plus and minus isomers of an optical active compound are called as an optical isomers, and the phenomena is called as an optical isomerism. So next our topic is a molecular asymmetry, then chirality or chirality, and enantiomers. So as we know that when any compounds who are optically active in nature, so how we justify what is the molecular asymmetry in this haloalkane or haloarene compounds. So for this purpose we definitely have an idea, because first time in 1848, right? The name of the scientist is known as Louis Pasteur. Louis Pasteur in 1848. who observed that the crystals of certain substance, particularly tartaric acid, such as sodium ammonium tartarate, exist in two different forms, which have exactly the mirror image of relationships. So these observations, which laid to the foundations of a modern stereochemistry, he demonstrated that the aqueous solutions of both the type of crystals rotated the plane of polarized light, okay, which is equal in magnitude but in opposite directions. Then after, Dutch scientist whose name is J. Van 't, and French scientist C. Libel. So they both independently in the same year, means in 1874, pointed out the same four valency of a carbon atom are directed towards the corner of a regular tetrahedron, and if all the atoms or groups attached to a carbon atom are different, so this carbon is called as an asymmetric carbon or chiral carbon. So how we judge that this compound is a chiral in nature or non-chiral in nature? So a molecule which contains a asymmetric carbon lacks of all elements of symmetry and is called as an asymmetric molecule. For example, if I take a different for example, in your textbook they give a certain types of the compounds, or they explain the chirality purpose. For example, in this case, right? So it's a non-chiral because this is the object, and the mirror image of this object is like that. Okay, if we superimposed, so it's the same image that we have to observe, because they are the superimposable mirror image are same. It means that this compound is non-chiral in nature. If the round or this round, so it's a mirror image of this circle is the same, so they are non-chiral in nature. But according to, for example, in our case of they given in a book, so it's a mirror image of our particularly hands and feet, right? So it's a different, okay. So this object is chiral in nature because they are non-superimposable mirror image, because this object and the mirror image which cannot superimposable to each other, right? So the same way in the case of feet. So there are various examples of this symmetric or asymmetric. For example, if I am having a English alphabet A, so mirror image of A, so it's a non-chiral in nature. But if I have a write R and it's a mirror image of R, if we superimposed, right, so we get such a type of picture. So it means that our compound is non-chiral in nature. So there are the various examples of this non-chirality that we have to understand. But now in the case of chemistry, so how we particularly judge if I having a CH, right? For example, this is hydrogen, same way, hydrogen and hydrogen. Okay, so it's a methane, but the mirror image of methane is definitely superimposable. So methane is not a chiral compound, right? So what's the definition of chiral compound? So objects which are non-superimposable on their mirror image are called as an chiral, and the properties of this non-superimposability is called as an chirality, while those which are superimposable on their mirror image are called chiral in nature. So ultimate test of chirality is the non-superimposability of an object and its mirror image, right? For example, if we apply this molecular chirality to organic molecules to check the non-superimposability, construct the model. First we have to either construct the model or draw the mind well three-dimensional structure. It's a stereo structure of organic molecules and their mirror image. Okay, and try to superimpose them, but this is a difficult test. A simple test for molecular chirality is the presence of a single asymmetric carbon atom in the molecule. Let us consider two different molecules. Okay, for example, if I having a propane 2-ol. Propane 2-ol means the structure of propane 2-ol is like that. C, once again C, OH, okay, 1 methyl it's behind the plane, one above the plane, one methyl above the plane, and hydrogen on the plane. So it's a one type of structure A. So what is the mirror image of this structure? The mirror image of this structure is like that. OHC, it's behind the plane, okay, it's above the plane, and hydrogen. So if we rotate, okay, fine, once again, if we rotate this image through 180 degree, 180, this is a structure A, this is a structure B. So we get the structure C is like that, C, OH, okay, then CH3, okay, CH3 and H. So we get a structure C. So propane 2-ol is a chiral because A and its mirror image B or C, both are superimposable. So they are, because this carbon is not chiral in nature. While this carbon is not chiral in nature, in simple manner, because two methyl same group are attached with this carbon. So what is a chiral carbon? The carbon who having a 4 different groups are attached with the carbon is called as chiral in nature. So definitely this methane, in the case of methane, is not chiral in nature. Same way it's not chiral in nature. Now one more example of butane 2-ol. So it's a COH. So same way here the CH3. Okay. So above the plane, for example, it's a C2H5 and hydrogen, right? And hydrogen. So it's a structure A, right? So what is the mirror image of this compound is OH, C, okay, CH3, then C2H5, and H. Okay, it's a structure B. If we rotate through 180 degree, so we get a certain image like that, COH, right? This is a structure of H, and it's a methyl group, and it's a C2H5 group. So it's a structure of ABC once again. So in this case, when you have to study about the butane 2-ol, so because your structure A and its mirror image either B or C, which is non-superimposable, because in a simple manner this carbon attached with a methyl, then ethyl, hydrogen, OH, all 4 groups are different, so they are called as a chiral in nature. So it's a chiral carbon. So from this discussion, we conclude that the presence of a single asymmetric carbon atom makes the molecule chiral. Hence, our compound is optically active in nature. That's why asymmetric carbon is called as a chiral carbon. So in chiral molecules, the asymmetric carbon or the chiral carbon is denoted by a ester stick, right? Other examples, for example, so if so it's a ester stick, so it's a chiral carbon in nature, but in this case it's not a chiral in nature. Same way, one more example is like that. For example, if I draw a structural formula, not a stereo formula of a compound, right? So it's a 2-chlorobutane. So in this case, 2-chlorobutane, your methyl is non-chiral in nature, your CH2 is also non-chiral in nature, and CH3 is also non-chiral in nature. But this carbon is chiral in nature. Why? Because here the carbon is attached with a 4 different group. One is H, remaining is Cl, and methyl and ethyl. So 4 are different in nature. So this carbon is chiral in nature, but the remaining all 3 carbons are non-chiral in nature. Same way, if we talk about this molecule, okay, so the name of this compound is 2,3-dihydroxypropanol, or sometimes it's called glyceraldehyde 2. So this carbon is chiral in nature? No. Why? Because this carbon is attached with double bond O, so no sp3 hybridization, it means no. Fine. This carbon is no, because carbon is attached with the 2 same number of hydrogen, so it's not chiral in nature. So okay, so yes, this is carbon, yes, it's a chiral in nature. Why? Because this carbon is attached with H, then OH, then CH2, and then CHO. So all 4 different groups are present. Same way, one more example which can be given like that, Br, CH, I, Cl, right? So in this case, your carbon is chiral in nature. Yes, this carbon is chiral in nature because this carbon is attached with hydrogen, iodine, chlorine, and bromine. All 4 functional groups are different. So definitely they are chiral in nature. Same way, if we get an answer like that, CH3, CH, Br, COOH. So one more example. But this carbon is not chiral in nature because it's connected with the 3 same hydrogen. Okay, this carbon is chiral in nature? No, because this carbon is connected with double bond O. Double bond O means sp2 hybridization, so it means that no tetrahedral structure is formed in this carbon. Okay, this carbon is chiral in nature? Definitely. This central carbon is chiral in nature because methyl, COOH, Br and H, all 4 groups are different. So they are called as a chiral carbon. So this is all about the molecular asymmetry, right? So after the molecular asymmetry, we have to focus about the enantiomers. So what is the meaning of enantiomers? What is the meaning of enantiomers? So in the case of enantiomers, so how we judge about the enantiomerism? So optical isomers that we have to particularly display in our portion. So optical isomers which are non-superimposable mirror image of each other are called the enantiomers, and the phenomena is called as an enantiomerism. The enantiomerism having identical physical and chemical properties. Both dextro and levo have a same physical properties, same chemical properties. So what is the difference between them? Because some people says that if the same physical properties like melting point, boiling point, dipole moment and whatsoever, right? And same chemical properties. So is it different? Yes, definitely it's a different because they rotate the plane of polarized light in an opposite direction, right? But same extent. If such a compound who rotate 18 degree clockwise, so its enantiomers means it's a mirror image is definitely the rotation is the same 18, but first one is plus 18, remaining is minus 18. First is called as an dextro and remaining is called as an levo. So in this case, the enantiomers have the identical physical and chemical properties but rotate the plane of polarized light in the opposite directions due to the same extent. For example, if I give one more example like that, if I having a C, then Br here, chlorine, iodine and hydrogen. Right, so it's a structure number 1. So what is the mirror image like that? So C, right? So mirror image is like that: hydrogen, bromine, chlorine and iodine. So to understand the phenomena of enantiomer, we consider with this example is a bromo chloro iodo methane, right? So which can exist in 2 stereoisomer form, 1 and 2, which are non-superimposable mirror image of each other. So further, each of the 2 isomers is optically, these both are optically active. They rotates the polarized light in the opposite directions but same extent. Thus 1 and 2, this represents the enantiomer of a bromochloroiodomethane. Similarly, when we have to study about in this case A and B, so they are the enantiomer of each other, right? If the enantiomer we rotate the planes of polarized lights towards its dextro rotatory, so it's called as a D plus, and rotate the plane of polarized light towards the left is called as a levo rotatory and it's a minus. So however it may be emphasized that here it's not possible to tell us to which isomer is plus or minus just by looking at the structure. It's not predict for the students as well as sir or whatever the persons who are connected with this stereochemistry. Not looking to the structure, we can judge this is a dextro in nature or levo in nature because it has been determined experimentally. So dextro and levo definitely we determine experimentally. So this is all about the enantiomers. Then we have to switch over to the next another portion is called as a racemic mixture. So what is the meaning of racemic mixture? A mixture of equal amounts of 2 enantiomers is called racemic mixture or racemic modification, right? Once again, a mixture of equal amount of dextro and equal amount of levo of the same structure, so it's called as a racemic mixture. A racemic mixture is always optically inactive even though they are having a chiral carbon. Why? Why they? Because the rotation caused by the molecule of one enantiomer is exactly cancelled by the equal and the opposite rotations caused by the same number of molecules of the other enantiomers. So which can be denoted by DL, because both having a same amount, DL or plus or minus. For example, if I have to display plus or minus, plus and minus butane 2-ol. Okay, so the process, another point is like that, the process of conversions of one enantiomer into a racemic mixture is called as a racemization. What is the process is racemic mixture, but if I having only dextro and then I have to convert into dextro into levo, and now we get a same amount of dextro and levo, so it's called as a racemization. Next, our point is retention. It's the most important point, right? What is the meaning of retention? Whenever a chemical reaction is carried out on a chiral molecule, the product may have the same configurations as the reactant, or may have the opposite configurations. If the relative space arrangement of bonds of an asymmetric center in chiral molecule remains the same before and after the reaction, so this is called as a retention of configuration. In other words, preservation of the spatial arrangement of bonds on an asymmetric center during a chemical reaction is a retention of configurations. So there is a one particularly molecule that I have to given. So if I have displacement reactions, so plus y and minus x. So what's the point? The plus y and minus x, it means that A, C, y and B. So there is a replacement of x and y. But mind well, in these reactions, retentions of configurations occur because the relative configurations of B, A, C, same way, B, A, C, from clockwise to B, A, C, B, A, C, okay, both in reactant and in the product is the same. So in general, if during a reactions no bond to the stereocenter is broken, mind well, no bond to the stereocenter is broken, right? The product will have the same relative configurations of atoms groups around the stereocenter that in the reactant. For example, if I give the example in like C, then CH3, this is the CH2, OH, same way, H, CH2, CH3, right? When it reacts with hydrochloric acid and heat is required. So as we know that it's not a chiral in nature, but this carbon is definitely chiral in nature, because ethyl, CH2OH, CH3 and H, 4 different groups are attached with this chiral carbon. Now the reactions is given like that, CH2Cl, okay, same here, CH3, okay, so in this case hydrogen, CH2, CH3 and water is released, right? So in the case of this, the name of this compound is 2-methyl-1-butanol, 2-methyl-1-butanol. When it is treated with a concentrated hydrochloric acid, we get a product 1-chloro-2-methyl-butane is formed. So in this, during these reactions, no bond at the asymmetric center is broken. So it's an asymmetric center is broken. Therefore, the reactions proceeds with the retentions of configurations, even though the sign of optical rotation has from, because experimentally it's a minus, plus, but there is no bond break, because the bond break is CH2OH, right? So it's called as a retention phenomena. So I think so you have a very much clear idea about the retention. So after retentions, now I have to mix all the terms: inversions, retentions and racemizations. Inversions, retentions and racemizations. So in this case, when we have to study about the inversions, retentions and racemizations, so whenever a chemical reaction, a bond is broken at the stereocenter, mind well, at the stereocenter, 3 things can be happen. For example, if I having such a type of example, right? So if we add a plus y, minus x, minus x, minus x, So in this reactions, for example, if I plus y, so there is a replacement of x, so here with a y. Same way here I have to add a plus y, so this is a plus y, and next is the minus x plus y. So all three possibilities are which can be given like that. So if only one is only product of the reactions, mind well, one is the only product in the reactions. So what in this case, the reactions process with the retention of the configuration, because it's a reservation. Okay, if 2 is the only product, so the reaction is to be the inversions of configuration, because it's almost invert the product. Okay, and if on another end, if we get a 50-50 mixture of one and two are obtained, this is called as a racemisation, and the product is optically, mind well, this product is optically inactive, because one isomer will rotate the plane of polarized light in the one direction and other will rotate in the opposite direction, but due to the same extent. So this is all about the inversions, retentions and racemisation. In next sessions, with the help of this stereochemistry, now we understand the stereochemical aspects of the nucleophilic substitutions reactions. Thank you very much.